Alright, hello class. Here's our first session of some extra examples from section 2.2, mainly some extra graph examples for those of you who'd like to see, a couple extra things involving limits. Okay, and so I'm just going to be looking at some of these limits here at these breakpoints and whatnot. Typically, the book or your online homework or the worksheets are going to specifically tell you, okay, find this particular limit, find that limit. But I'm just going to start, say, here at 1. So I'm going to start, let's say, with the limit as x goes to 1 from the right of f of x. Okay, so let's say this is a graph of f. Okay. Now, what we're going to do is, so remember, this is my x value I'm looking at, 1. And this plus sign means I'm coming from the positive side. I'm coming from the right. So again, I usually start about halfway, right? So we're coming in this direction, right, from the plus side. And I start mapping up to where the function is. And we can see these points I'm plotting on the graph are getting closer and closer to this open circle here. Again, one nice way to do it is to just cover up the left side, right? Because we don't actually need it. And what is the graph itself getting closer and closer to? It's getting closer and closer to this open dot, which is 1. So the limit from the right is equal to 1. Okay, on the other hand though, if we look at the limit as x goes to 1 from the left, or from the negative side, so now we're looking at it from this side, okay, coming in this direction. So again, I start about halfway away, 0.5 on the left, and I start getting closer. And as I do that and map up to the function, wherever the function is, and again, we can cover up this other side if it helps, but we see these points I'm plotting are getting closer and closer and closer to this open dot here, and this is actually 2. Okay. So the limit as x goes to 1 from the left is actually equal to 2. Now, these don't match, right? So the limit as x goes to 1 of f of x, right, from both sides, right? If I don't have a plus or minus, that means both sides. Well, they don't match, right? From either side. So this does not exist. Okay. And then finally, if I look at f of 1, right, this is when x is actually equal to 1, right? Here, this is, right, from the right, this is when x is actually greater than 1. From the left, this is actually when x is less than 1. And this limit is from both sides, but, both sides of 1. And this is when x is actually equal to 1. And when x is actually equal to 1, if I go to 1, okay, and map up to where I find a point on the graph, well, I don't have a point here because that's an open dot. I don't have a point here, open dot. If I head on up, oh, there's my closed dot. It's all the way up at 4. Okay. So this is a very discontinuous place here. I mean, we have a jump discontinuity and a removable discontinuity because we've moved the point up. Okay. And let's look at now the limit as x goes to 3. Okay. Actually, let's let's look at all the sides here. Okay, so let's look at the limit as x goes to 3 from the right of f of x. Okay, so the x value we're looking at here is 3, and I'm coming from the positive side, right? So I always start about halfway there. You can always, look really closer, and you're just kind of seeing where the graph is going. And again, if it helps, you can just cover up the left side and just see what's going on here. And we map this up, and we get these points I'm plotting on the graph, right? Plot the points on the graph, and they are getting closer and closer to this point here. And that y value is right on the axis, so it's 0. So the limit from the right as x is going to 3 is 0. Okay. Let's look at the limit as x goes to 3 from the left. Okay. And many of you probably, just looking at this, already have that, oh, it's going to the same thing. But again, we're coming from the left this time. Let me erase some of this stuff over on this side just to unclutter it. But we're coming at 3. Now again, I've had many people who start looking at things way over here. Don't. You're looking at things close to 3. That's the whole point of limits, right? Is be really close to 3. So I usually start around here and start plotting my points. And if it helps, you can, like I said before, cover it up completely, or the right side. And these points that I'm plotting on the graph here are getting closer and closer to this point at 0. Okay, so like I said, the limit as x goes to 3 from the left of f of x is also 0. Okay. Then the limit as x goes to 3 from both sides. Well, does everyone see that it matches from the left and right? They're both 0, so the limit on both sides must be 0 because it matches. Okay. And what about f of 3? And remember, this is when x is equal to 3. I keep saying that, but I want to really drive that home, that there's a big difference between the limit as x goes to 3 and f of 3, which is when x is actually equal to 3. So limits, x does not actually equal 3 at these places. Right? You're just really, really close, really damn close to 3 at these places. Okay. And f of 3, well, when you actually look at 3, and we actually have a closed dot there, which I put because the graph looked a little funky without it, just the graphing software. That's why I put a point there. But we have it's equal to 0. So all 4 of these options here are equal to 0. We have a limit from the left and the right match, which means the limit from both sides exists, which equals the function value, matches the function value, so that they are all the same. All right, one last thing I want to look at is I want to just go straight. Instead of looking at both sides, I want to look at the limit as x goes to -1 of f of x. Okay, so -1 is all the way over here, right? And it's the limit from both sides, right? So all we do in this case is you just look at both sides, okay? Both sides. So I map, say from the right, I start about halfway there and start mapping points up. And these points seem to be getting in closer and closer to this point right here, okay, at 4. And now that's from the right. And we can see the same behaviors happening on the left. If I start here and start mapping points up, we get closer and closer and closer to this point here, okay, which is a y value. Remember, we're looking at y values of 4. So the limit as x goes to -1 of f of x is 4. All right, what is f of -1? Well, we really only see this one point here. It's not an open dot. We just see a nice continuous function there. So the limit and the function value match here and give us 4. All right, let's look at another example. All right, next example is a little more complicated, but we have 2 breakpoints instead of really just one. But, so we're just going to go through and take a look at these, at the breakpoints and maybe various other spots. So let's start with the limit as x goes to -1 from the right, from the positive side, and let's call this guy g of x, just so we don't use the same letter all the time. Okay. So -1, that's, remember the x value we're looking at is right here, so I'll go ahead and shade that on up. That's what we're looking at, and we're coming at it from the right. The plus sign means from the plus side, so we're going in this direction from the right. And so again, we're trying to get to 1, excuse me, -1. So I'll start here at about -0.5 and start mapping things up from there. And I don't know, it helps me to actually put little points on there when I'm, when you're first learning this. And again, as I've always said, you could just block this off and see that these points on the graph here, as x gets closer to -1, the y's are, making their way up this line towards this open dot, which is at 3. Okay, so the limit as x goes to -1 from the right of g of x is 3. Okay. From the left, if it helps, from the left, we'll start here at -1.5 and start getting closer. And I will say with limits, -1.5 is way too far away, really, realistically, like if you're making a table or looking at values. But on a graph, it's a nice place to start, but it doesn't tell you anything. Limits involve movement. That's the way I like to think of it. It involves x moving closer and closer from a starting point, and here we're on the negative, coming from the negative direction towards -1, and there's movement. X is getting closer and closer to -1, and as that happens, these points are getting closer and closer and closer to this point right here, which happens to be a y value of 1. Okay, so the limit, I didn't write it down, but the limit as x goes to -1 from the left, so this is from the negative side, so remember this is your number, this is your direction, so that limit is going to 1. Now, what can I say about the two-sided limit given this? Well, does not exist. Why is that? These two don't match, right? The limits from both sides have to match for the limit itself to exist. All right, now, like always, now I'll look at g of -1. Now, what is the actual function value at -1 when x actually equals -1? Well, we're looking for the closed dot, and the closed dot is right here at 1. Okay. So one thing I want to say is that the limit does not exist, so the limit and the function value don't match. But the function value does match the limit from the left, and that's because we have the closed dot on that portion of the graph. Fair enough? Okay. Now, sometimes, we looked at this on the last example as well, sometimes they just ask for the two-sided limit, right? So let's say I just ask what's the limit as x goes to 3 of g of x. Well, here's 3. And when you start doing this enough, you can actually just kind of jump right to the answer. Because look at this, we have a jump. If we have a jump, the limit does not exist there. The two-sided limit does not exist there, right? So I can go all the way just straight to does not exist, right? We have a jump. But you can also just check both sides. This is a two-sided limit. So starting at 3.5 and going towards 3, we map up to this portion. And again, we can cover this up. And the points I plot over here, when I do that, are getting closer and closer to this open dot here, which is at 4. Right? So the y's here are going to 4. Okay? But on the other side, right, at 2.5 and heading towards 3, the points are getting closer and closer instead to this open dot, okay, which is at 2. So the y's on this side are getting closer and closer to 2. So from the right, the y values, or g, is getting closer to 4, while on this side they're getting closer and closer to 2. They don't match, right? They don't match. Okay? So whenever you have a jump, right, a jump discontinuity, where the graph jumps, the limit's not going to exist there, right? Why? Well, because for a limit to exist, the left and right limits have to match. They have to be approaching the exact same thing on both sides. Okay? It would have to be something like this, where, say here at 1, where if I looked at, I'll write it up here, the limit as x goes to 1 of g of x. Okay? Well, on both sides, right here, let me do this one in red. Do you see that the function on both sides meets this point? We come up this way, come up this way, right? And you can, apply the points like usual, like from the right and from the left, and see that they're both zeroing in on this y value, which looks to be about 2.5, right? Just about. Okay. So from both sides, that graph is zeroing in on 2.5. So I'm going to go ahead and just estimate here that the limit as x goes to 1 of g of x is 2.5. But where I have a jump, the limit does not exist. But the left and right side limits do, right? From the right, that limit would be 4, and from the left, it would be 2. Now, what about, let me look right here, I've got some room. How about g of 3? Okay. G of 3, well, if we go back to 3, where is our closed dot? It's right on the axis, 0. Okay. So this one, the function value doesn't match either sided limit. All right, so there's 2 more examples from 2.2. Hope you found that useful. Again, we'll be having our worksheet on this soon. But hope that helped, and take care.